Hello and welcome for today's session. So today we are going to learn on tributary loadings. The tributary loadings are actually the loadings coming from the floor system or a roof system, and this system are surface elements that are attached to structural or line elements. So we should know how to distribute these loadings because it will be our basis in idealization of our structure. So there are actually two system of tributary loadings. So the system could be number one, it is one-way systems, and we have also two-way systems. So what is the difference between one-way system and two-way system? So if we have a one-way system, there is a significant difference between the short and the long dimension. So to illustrate that, let us consider here certain slab. Okay, say this is the slab. There will be two dimensions for this slab. Say we'll be having along the direction and the length along the short direction. So in one-way slab, we'll just have the criteria L over S should be greater than or equal to 2. So this is for the one-way system. Okay, so what about the two-way system? The criteria is that the longer dimension divided by the shorter dimension is less than 2. So this now becomes the two-way system. So if we are going to investigate the equation here, there will, in one-way system, there is an obvious difference between L and S. So S is much longer significantly by S. Okay, so if we are going to illustrate that, a one-way system look like this. Okay, so this is the orientation of a one-way system. So there is an obvious uh, difference on the length versus the on the long dimension versus the short dimension. So the rationale here is that the reinforcement is more on the longitudinal section. Okay, so when we say longitudinal, the reinforcement or the loading is being carried more by these two support. Okay, by these two support. So actually, these supports will carry the loadings. And for the distribution, of course, it will just be divided by 2. Okay? Say if we have here a beam, say I'll just label this as B1 and this is B2. Okay? The tributary area that will be carried by B2 is this shaded portion. Okay? So this red portion here is the tributary area that will be carried by beam 2. And then of course, the other one, this yellow area here, or the other pair of the slab will be carried by the other beam. So this is one-way slab. In short, along the longitudinal direction or the longer span direction, the tributary area will just be equally divided to the adjacent beam along the long direction. If you have to ask me, what about this beam on this edge? So on this edge has no significant uh, contribution when we talk on one-way slab. So the purpose of this edge is just to enclose the framing system, but not actually carrying a portion or any portion of the slab here. So whenever there will be an adjacent slab attached to the beam, for example, we have another adjacent slab here, another two-way slab here. So again, we are going to divide that one. This is being carried by the beam here. Say B3 and B4. So again, B4 will be carried by, or will carry the half portion of the slab on the longitudinal direction. As we can see, it will just tend to stiffen our framing system, or the sub beam here or the transverse beam here. These beams would have a minimal carriage of the loading, and the loading again is distributed more on the longitudinal beams along the long direction, say B1 and B2, B3 and B4. So the distribution is just simply split the slab along the long direction, or the splitting would be on the short direction and then distribute it on the long direction. So that is the principle of one-way system. So in reinforced concrete, we wanted to have a one-way reinforcement, meaning the reinforcing steel bar is just concentrated along the long direction. So how is that one? So we're going to have the reinforcement. So this is a top view. The reinforcement will just be concentrated along the long direction. So if we wanted to have a longitudinal or transverse reinforcement, this transverse reinforcement is purposively only to have a temperature bar in order to have a bar that will put in place these longitudinal bars. Okay, so that is for one-way system. Okay, so let us now proceed. What about two-way systems? So for two-way systems, we'll just have this criteria. Okay, so L over S, or the longer divided by the shorter span, is less than 2. So the figures like this, there is no obvious or great difference between the longer to the shorter span. Unlike on the one-way slab, there is an obvious difference on the longer versus on that shorter span. Okay, so how is the distribution now? So illustrating that one, so illustrate that one. So if this is our slab, okay, so it looks like a square. It is more on a square shape, but there is a slight difference between the longer and the shorter span. Or it may be that the longer or both dimensions are equal, there will be no longer and the shorter span. It could be that it equal. In short, in two-way system, we have more on a square shape. On the one-way system, we have a rectangular shape, an obvious rectangular shape. So the distribution is that we'll just have to get the edges here. Okay, of course, this is assumed to have beams here. Okay, these lines represent beams. Okay, a framing for a beam, and this is a floor. This is just an example. So we have to create a line that is 45 degrees. Okay, this is 45 degrees, that is 45 degrees, and this is another 45 degrees. So just create a 45 degrees line on the edges and then project it until this will intersect. Okay, and close that line by a horizontal line. Okay, so here we can see now, if we have some beams here, say this is beam 1, this is beam 2, say that is beam 3, and that is beam 4. We have now the tributary area shaped like this. So this will now be our basis in determining the area. So of course, if we have here a 45 degrees, we will now get the area because this is a trapezoidal area class. We shade that one. So this is the trapezoidal area. of the shape. Okay, so if we need to determine the tributary area, we'll just have to get this trapezoid. So how is that? First, we'll just have to create here a line to form two triangles and one rectangle or square, perhaps. So we get the dimension. How shall we get the dimension? Of course, B1 is already there on the longer base of the trapezoid. What about this dimension? Okay, so that dimension is actually subtracting, okay, this horizontal dimension here. So B1, say if I'm going to label this as X, okay, say this is Z dimension. So in order to come up with the Z, of course, we just say that B1 is the sum of 2X plus Z. So we know X here, X could be determined by this triangle because this is also 45 degrees. So we have here a right triangle, and of course this dimension is already known, that is B2 or half of our B2. So when we know this one, we can now get this value. So this is similar to the other side, okay? So B1 is known, X is known. We can now determine our Z, and if we know Z, then we can now get the area for trapezoid. Okay, so this is the tributary area for B1. And what is the area for trapezoid? It is 1/2 the average of the bases. We have Z plus B1 all over 2 multiplied by the height, and the height is B2 over 2. So this is just a representation of our solution. You do not have to memorize this one. What is important is the principle. Okay, so what will be the figure how is the beam look like, or how is the loading look like with regards to the distribution on the beam? Say this is our B1, okay, this will be our B1. The distribution is, this is a trapezoidal section distribution, okay. We have here a trapezoidal distribution of this along B1, okay. So how is it done? When we have here a pressure, say for example, the pressure is in terms of kilonewton per square meter, uh, we multiply it by the tributary area, square meter also. Then we come up with the kilonewton unit, right? And the kilonewton unit here will now be distributed along the length. So we have, and then we wanted to divide this by B1. So thereby, if this is W, this will be in kilonewton per meter. So you might ask that what is the divisor here? W is equal to, from here we have kilonewton, or the first divided by B1, that is meter. However, let us have to X this procedure. Why? Because upon determination of the kilonewton here, we have linearly divided it by meter. Okay? Well, in fact, it's not. Okay? It's not divided by a. It should be that we should consider here the peak. Say this is the peak value of W. Why we say peak value? Because it is 0 here, okay, up to the peak. So we have a trapezoidal distribution. So the correct procedure here is that, illustrating again the figure, say here's the slab. We will first simply assume that the distribution is on the longitudinal section. This is the longitudinal section. We have here the longitudinal section. We'll just have to divide that, or split along the long direction, just as the principle on the one-way slab. We're gonna split that one and consider this again as our area. Okay, this is our area of consideration. Say if this is B1, say this is B2 over 2. B1, this portion here is B2 over 2, or the half of B2. B2 all over 2. So therefore, if we have a pressure, say the pressure is equal to kilonewton per square meter. So what we do is to compute for this tributary area. Tributary area is equal to B1 times B2 over 2. That will yield to a square meter, of course. Okay, so we multiply that by that one. So therefore, this is cancelled. We come up with a kilonewton, and W here is equal to the pressure times the tributary area divided by B1. Okay, so therefore, this is the peak value now. Okay, so this is the peak value. So this is equal, if we are going to look at the distribution of B1, assuming that we have a one-way slab, we have here a uniformly distributed load for a one-way slab. So we obtain this peak value here. Okay, this shall be adapted to the two-way slab, wherein we'll just have to redraw this one. We'll use the trapezoidal distribution. Okay, so this is also W. Okay, so that's how to get that one, not by merely determining the area here and then multiply it by the pressure and then just simply divide it by V1. So that is a wrong solution. Okay, so let us have a concrete example on this one so that we can have a clear view on the procedure of the distribution of two-way slab. No problem on a one-way slab because we'll just have to split the floor into two and distribute it to the framing system on both ends of the slab. So if we have here a two-way slab, if we have here a two-way slab, so this is the two-way slab. Say we're going to label this if this is equal to 15 feet and this is equal to 10 feet, we will create here a 45-degree line. It will look like this first. So again, do not do this calculation wherein you are going to calculate this area and then multiply it by the live load. Say for example we have a floor load equivalent to 100 PSF. You might do this way. So this is 45 degrees, this is 45 degrees again. So we'll just split 10, that will be equal to 5, right? 5. So if this is 5, 5, this is also 5. Okay? So if this is 5 and 5, that is 10. 15 minus 10, this is 5. You might do it that you might get the area of this green portion here. 15 plus 5 all over 2 times 5. So this is the area of a trapezoid. We have 20 over 2, 10 times 5. We have 50 square foot. And you might get the W. For example, this is our beam. And this is the distributed load. Let us have the following dimensions here. This this is actually 5, 5, and 5 to make that 15. So this is our W now. For distributed load, you might do it this way. Again, this is a just a presentation. You might do it that W is equal to 100 pounds per feet, and you eventually multiply that by 50. So we'll be having here 5,000 pounds divided by your length, that is 15. So 5,000 divided by 15, we have 333.33 pound per feet. You might do this. So I would like to reiterate, or just presenting the solution, that this is wrong, because again 5,000 here came from a trapezoidal area here and then linearly divided by 15. We cannot divide it linearly because this is not linearly distributed also. This is not uniformly distributed all over the length. So when we say all over the length, the distribution is that it should be assumed that we have the peak level here, okay, all throughout, not a declining force on both sides until it will reach 0. In short, 15 could not be linearly divided by 5,000. So I would like to emphasize that, okay? So the correct way to do this is to divide your slab, or split it along the short direction, just like on the one-way slab. Okay, so along the long direction. Okay, so along the long direction, of course, the area, if this is 15 by 10, 15 by 10, 15 times 10 is 150. So there will be a 75 and 75 here. Okay, so this is the area of coverage, right? So 15 by 10 all over 2, or you may have it 15 times 5, which is also 75 square meter. Of course, the pressure loading is equivalent to 100, and if we are going to get W, we have here 100. This is pounds per square feet. 100 pounds per square feet times, sorry, this should be in square feet. We are in English. Okay, 75 square feet. Now this is cancelled, becomes pounds, or a unit for weight. So we wanted to distribute it on the 15 feet length. So what you do is to divide this by 15. So basically, 100 times 75 divided by 15 is 500. So this is 500 pounds per feet, which is actually the correct peak value for W. When we say peak value, we are now correct to divide here 15 because 100 is equally distributed to 15. Okay, 100 is equally distributed to 15. Unlike here on the trapezoidal portion, 100 is not equally, or 100 times 50 or 5,000 is not equally distributed to 15 because in the first place it is of trapezoidal section wherein these edges is declining. Unlike here, when we illustrate that one, here's the beam. This is a flat line. Okay, so it is what, 500 or 100 times 75, 7,500. Okay, this is the result. 7,500 now is equally divided to 15. Okay, 7,500 is equally divided to 15. So that is how it works. That is why 7,500 divided by 15, we have 500 pounds per feet. So this is the peak value. Wherein if we are going to illustrate now the distribution of our slab is like this. See, this is our slab. This is 15 and that is 10. Just draw a 45 degrees there. Draw a 45 degrees. So if this will be our beam, we have here the trapezoidal distribution of the loading along B1 or say B2. So of course the dimension of this is 5, 5, and we're gonna use the peak value that was obtained in assuming that this is split half. We have the peak value to be 500 pounds per feet. Okay, so therefore on this side also, if we have to consider that 10 feet on this side, say this is B1, I'll just label this to be B3 and that is B4. So if this is B3, our concern is just the peak value. Just have the peak value at the center. Okay, this is 500 pounds per feet. Okay, so the shortcut method here is simply just multiply the pressure. So W is just multiply the pressure on the two-way slab or the two-way system. In any two-way system, W is just simply equal to the pressure or the floor pressure multiplied by the half of the shorter distance. Okay, pressure times the half of the shorter distance. So let us test that one. The pressure here is 100, right? And the half of 10 is 5, or 10 over 2 is 5. So we have now 100 times 10 over 2, that is equal to 500 pounds per feet. So this is the peak value in which we have used that on the trapezoid and the triangle respectively. Okay, so another example. What if we have an equal dimension for a slab? Therefore, this is now a square, look like a square slab. Say this is 10 by 10, 10 by 10. So again, if our floor load or the pressure is equal to 100 pounds per square foot, so the shortcut version, again, if we are going to have here a 45 degrees triangle, it will have to intersect at one common point because we have an equal dimensions. Okay, it will just intersect at one common point. So if this is labeled as B1, B2, B3, and B4, they have just equal distribution. And thus the beam looks like this with a triangular distribution having this as the peak value for W. So what was the shortcut version of W? W is equal to just multiply the pressure by the half of the shorter dimension. But here it appears to have an equal. We do not have any shorter dimension. So just adapt that dimension, 10 over 2. So 10 over 2 is 5 times 100 is 500 pounds per feet. So this is the beam distribution on B1, B2, B3, or B4. Okay, so that is the principle or the shortcut for that. So do not bother yourself in computation of the areas of the surfaces according to the lines or the constructed lines that is projected 45 degrees on the edges. So what you just do is that solve for the pressure and then the shorter distance divided by 2. So if your distances are equal, or the dimensions are equal, therefore just adapt any of those and divide it by 2, multiply it by the uh, pressure. Okay, so let us have a summary for that. So for one-way slab, we have obviously a rectangular section wherein L is obviously longer to that of S. So meaning, if you double S, it will be equal to L, or it is still shorter than L. Therefore, the criteria is L over S is greater than or equal to 2. Okay? For example, this is 5. If your S is 2.5, then that will fall under one-way slab. But if your L is 5 here and your S is 3, that will fall under two-way slab already. Okay? And computing for the distributed load for this one-way slab, W is simply equal to the pressure times the tributary area. What is the tributary area? L multiplied by S all over 2, and then divide it by the length where you wanted to distribute it. And again, I would like to emphasize that S here would not carry any portion of the slab because we are in one-way slab. So the main member that will carry it is the longer beam, not the shorter beam. Okay? So contrary to two-way slab, all beams will have a portion of the floor to carry it. We have two-way slab here. If we have a two-way slab, it will look like more on square type, but there will be a slight difference on L over S, wherein the criteria is that L over S is less than 2. As for the distribution, again, we are going to create here a 45-degree lines on the edges so that on the longer span, beam at the longer span, we have this beam and a trapezoidal loading utilizing a peak value for W just simply equal to the pressure times the half of the shorter dimension. Okay, so on the shorter dimension, beam on the shorter span, we have this. Let me have this as L and that is S. So we use the same W obtained from multiplying the pressure times S, or half of the shorter dimension. Okay, so that's it for tributary loadings. So please stand by for more examples on this topic.